But okay, so let's start with today's seminar, colloquium. So let me very briefly introduce Sander Otte. I think most of you know him anyway. So Sander, he's got his PhD from Leiden, 2008. And then already during his PhD, he was visiting Andreas Heinrich at the IBM Almaden Research Lab. It seems that it was a very good visit. There are some very prominent papers from the time, Science, Nature, Physics, so on. And that's when I think when Sander got started with this STM and spin system stuff. After IBM, Sander was at the NIST with Joe Straussio for a couple of years as a postdoc. And after that, at 2010, he returned to Netherlands, to Delft, where he's been leading a research group ever since. So he's now the Anthony van Leeuwenhoek Professor at the Department of Quantum Nanoscience in TU Delft. And well, as you know, Sander works on using scanning probe microscopy, scanning tunneling microscopy, and atom manipulation to create all kinds of atomically well-defined structures. And one of the focus topics, and I believe it is the focus topic of his group, is to position individual magnetic atoms to study quantum magnets. And today he will discuss the tremendous recent progress in this field in building, probing, and understanding various coupled spin geometries. And the title of his talk is Non-Local Detection of Collective Atomic Scale Spin Dynamics. So I think with that, Sander, please.
Thank you, Peter, and for this introduction, first of all. And I also really want to thank both Peter and Jose for taking the initiative to start this colloquium series. I think this is exactly what we need as a field, not only during this crisis, but as Daniel already pointed out a minute ago, also for beyond. I think we should move to more online meetings. So let's see how this works, and I'm very positive about it. So also thanks for the confidence of giving me the first talk, both thanks and not thanks, but it's okay. I'm very willing to do it. So yeah, here we are. And I will talk today about a few things. But the most important thing that I will mention is the non-local detection of collective atomic scale spin dynamics. And you see this interesting picture here on my title slide, where I've drawn a chain of magnetic atoms, as we study so often, and then with a mousetrap on it. And this is supposed to depict the following. Imagine that you would be interested in studying the dynamics of a spin chain. This means that you start with a spin chain in a certain ground state, and then you make an excitation somewhere, and then you're interested in how that excitation, that quantum excitation, travels through your spin chain. That, I think, would in itself be an interesting thing to study. The problem is that with an STM, you have only one probe tip. It is so far impossible to get a second probe tip close enough that you can both have them on an atomic scale structure. So you have one probe tip, which means that if your probe tip is somewhere here on the left to make an excitation, it can never also be somewhere at the right to check whether that excitation actually makes it there. So you need to play a trick. You need to put some sort of a trap, like a mousetrap, that is triggered at the moment that an excitation passes by and then snaps, and then it stays snapped, so that seconds later you have time with your STM tip to go there and check whether the excitation got there. And so that's the key idea. You make an excitation at one spot, a quantum excitation. The quantum excitation travels at a tremendous time scale, much faster than any STM tip could move. And then it either triggers or does not trigger a trap, and then you can later, in retrospect, check whether it got there. That's the idea. Okay, I'll of course explain that in way more detail in a moment. Let's first give a bit of an outline. So since this is officially a colloquium, and since I'm the first speaker in the series, let me just spend a few slides on a general overview of our field and remind us again, why are we doing this and why is it interesting? Just a few slides. Then the main dish for today will be the non-local detection of spin dynamics, what I just introduced. And then as a dessert, I have another work that is about a single atom, where we demonstrate that we can not only make spin excitations, but also independent excitations of the orbital momentum, where we completely reverse that orbital momentum. And just as a bit of a teaser, that excitation that we're looking at is a delta m equals 4 transition, which at first sight might seem impossible, but actually we think it is very well possible. So that's a bit of a teaser. Okay. So spins on surfaces. So the general idea of our field is that we use an STM to position individual magnetic atoms on a surface. This can either be a metal surface or a metal surface with an insulating layer. There's also experiments on semiconducting surfaces or superconducting surfaces. There's all kinds of variations. And this is interesting because once you start to build these spin structures, you get fascinating physics because you have a competition between all kinds of various energy scales. So let's review the different energy scales, or some of them, that come into play. Most importantly, you have the Zeeman effect, right? So if you apply a magnetic field, an external magnetic field, this will cause a Zeeman term in your Hamiltonian, and spins that are aligned with the field will be lowered in energy, and spins that are anti-aligned will be raised in energy. So this is a linear term in your Hamiltonian. Another one is the interaction between your atom and the crystal that it is embedded in. So if you put an atom on a surface, so a free atom can point in any direction and it will cost the same energy. But if you put it in a crystalline environment, the spin might favor certain directions over others. And there's all kinds of different ways to express this in the Hamiltonian. I'm writing here a very general form where I'm looking at the actual and the transverse second order terms, ds(z) squared and e sx squared minus sy squared. So in general, this means that if, for example, your d term is negative, you will have a spin system that likes to point all its magnetic moment along a certain axis. So then, for example, you favor, in this case, the plus or minus, well, what would it be, plus or minus 3 over all the other states. The problem is that the transverse term over here, the Sx and Sy terms do not commute with Sc, so you can rewrite this in terms of your raising and lowering operators. And as a result, the E term actually causes mixing between your Sz eigenstates. So that looks like this. You get kind of mixing between these states. Your actual eigenstates become superposition. And the higher you're up in this parabola, the stronger that effect is. So this already becomes quite interesting and quite quantum. Then there's a third energy scale, which is the coupling between neighboring spins. So you put two atoms next to each other on a surface, and if they're close enough, they might feel each other due to all kinds of physical mechanisms. Most importantly, exchange interaction, if you're really within tunneling range almost. RKKY interaction through the underlying metal, or dipolar interaction. And so depending on the exact configuration, one might be stronger than the other. But in general, very often this can be written in a term J S dot S. Actually, dipolar is a bit more complex. Doesn't matter for now. It's J S dot S is the Heisenberg interaction term. And also here, this Heisenberg interaction term, you can rewrite in terms of Sx, Sy, and Sz operators. And the Sx and Sy you can rewrite into your raising and lowering operators. And also this causes entanglement between neighboring spins, and even longer distance entanglement. Even if your interaction is only nearest neighbor, you can have long distance entanglement between spins. So the physics really becomes quite interesting. And then lastly, in an STM configuration, you will always have the interaction with the underlying metal. So there's all the electrons in the bath that try to screen your spins, and this results in collective physics phenomena, which in general we describe by the Kondo interaction. Okay, so that is kind of the idea. To give you a few examples, so there's a famous paper by Alex Kajaturians in 2012, where there are several iron atoms on a metal surface. And here is a beautiful example of where the Zeeman interaction competes with the spin coupling. So at low fields, the spin coupling dominates and you have anti-ferromagnetic configurations. And then as you increase the field to the right here, at some point, all the spins surrender to the field and start to point out of plane. However, in this particular experiment, there's another energy scale, the anisotropy, which is actually dominating over everything. And as a result, these are really large magnetic moments pointing either fully out or fully into the plane. And the other magnetic moments are at much higher energy. So it becomes a little bit more like an Ising system. And as a result, these entanglement terms, so these do not really play a role here because they only work when you have spins 1/2. So you really, in this situation, do not get long distance entanglement between the spins. Now, a few years later, we had a similar paper where we actually did something else. We used a similar, let's say, competition between coupling and field. But in this case, we had spins 1/2. So in fact, also here, the anisotropy was strong, but it favored the plus or minus 1/2 states. And then you do get these long range entanglements. So this is chains of up to 9 atoms. You see here spectra taken up to 6 atoms. And the interesting thing here was that as you approach the critical field beyond which you are in the paramagnetic phase, so that would be similar to this phase where all the spins point out of plane, before that, you cross through various different ground states. And each of these ground states can be classified by the number of so-called spin-ons inside the chain. Spin-ons are collective quantum excitations that result from all this entanglement. So let's have a quick look what it exactly is, a spin-on. So a spin-on is
Sander, just
yes.
one thing. So there's one question by Vincent.
Yeah.
So Vincent, you can talk.
Yeah. Can you please explain what we see on the STM images of panels D to H in this slide?
Yeah, so on the left here in the STM images, we are looking, it's a very good point, at not just topography, but at spin polarized STM. So I should have explained that. So there is a few techniques that we have at our disposal in STM to look at the magnetic states of atoms, and a very important one is spin polarized STM. So the idea is that you have a magnetized tip, and as a result of that, the current coming from the tip, the tunneling current, is spin polarized, which means that there is a majority and a minority spin state. And that means that depending on the orientation of your magnetic atoms that you're probing, you get a different contrast. So for example, over here, you see white atoms and dark atoms that may correspond to spin up and spin down, and you see something similar here. Here you don't see the contrast, but that's because all kinds of different states are degenerate, and on average you don't see contrast, but in each of those states there would be a contrast. But if you go to a very large field, all the spins point along the field, and then your contrast is gone. So that's here on the left. Then on the right here, I'm using a different technique. This is inelastic electron tunneling spectroscopy, and here you look at spin excitation as a function of the energy. So yeah, I really have to explain this a bit better. So each of these squares here shows on the vertical axis the voltage that we apply on our junction, and on the horizontal axis the field up to 9 Tesla. And then every time so these are all kinds of different spectra taken and pasted next to each other. And then every time you make an excitation on the spin, so you offer enough energy for the electrons to kick the spin out of the ground state into an excited state, you see, well, to put it simply, you see a feature. So in this case, that would be a dark line here. So this dark line corresponds to the fact that at that field, at that energy, you can make a spin excitation. And interestingly, so this is for a chain of 4 atoms, a spectrum taken on the first atom, second atom, third atom, fourth atom. You see that these excitations happen at different energies. And from that, you can read off in which ground state you are, because the ground state in which you are tells you which excitations you can make. I hope that roughly explains what we're doing here. Yeah, I should have explained this a bit better, but I do want to point out that you don't need to understand all this to understand the rest of the talk. So this is also a little bit for people that have seen this paper before. I just wanted to focus on the physics that was being studied. Okay. Yeah, let's move on. So what are spin-ons? So spin-ons are collective excitations that happen in spin chains, and they're actually quasi-particles. So a spin-on would exist in an anti-ferromagnetic chain. So this would be the ground state of the chain. But a possible excitation in an anti-ferromagnetic chain is that you make one bond, let's say higher energy. So you make two adjacent spins parallel. So you basically go from one Néel state to another Néel state, and there's a domain wall here. That would be a classical, domain wall. But then it becomes quantum because the spin-on, the domain wall, can simultaneously be at all different positions in your chain. So it becomes really like a particle that has a wave function that can be, that has different A1, A2, A3. So it has different weights and a different distribution over the chain. And as such, it is a particle. And so the number of these particles, they are spin 1/2 particles, is the same number that is plotted here in each of those states that live inside the chain but are completely delocalized in the chain. Another typical and related collective excitation is the so-called magnon. A magnon is actually a spin 1 excitation. I've drawn it here on a ferromagnetic background, but it can also exist on an anti-ferromagnetic background. So here you flip one spin, so basically you create 2 frustrated bonds. So it's basically 2 spin-ons that are glued to each other. And also here you can draw a wave function. So a magnon, also called a spin wave, can be delocalized along the chain. So I've already shown how we can see spin-ons in our work. We can also actually observe magnons. So this was a paper we had in 2014 on a chain of ferromagnetically coupled atoms, so six atoms here in a chain. And then again, the anisotropy here causes ground states of 2, 2, 2. So each of these iron atoms is a spin 2 system because there are 6 spins in the d orbital, 4 of which are uncompensated. So you're a spin 2. So the ground state is either 2, 2, 2, 2, 2, 2, or -2, -2, -2, -2, -2, and that's because of anisotropy and ferromagnetic coupling. But then the excitations that live on top of these ground states and other metastable states are so-called spin waves. And here we have plotted those. So on the left here you see measurements. These are again excitation spectroscopy. So here the spectra are again vertical. The color scale shows you the excitations at different energies. And here on the horizontal axis I have the 6 atoms in my chain. So they're all measured at the same field. So 1, 2, 3, 4, 5, 6 atoms. But then you see a pattern here emerging. And that pattern you can understand here also in theory in terms of spin waves. So if you look at this pattern, and which is the same pattern you see here, you actually recognize the first 3 spin waves. The first of which is completely delocalized. It's called the ferromagnetic resonance. And then you have one that has a node in the middle, so no weight in the center, but 2 antinodes at the sides. And then you have a spin wave that has an antinode, a node, an antinode, a node, an antinode. So you really can see those spin waves or magnons in such a chain. Okay, so that was what I wanted to tell in terms of general introduction to spins on surfaces. Now, let's go back to the idea that we had. We want to do remote detection, and as I explained in the title slide, we want to have some mousetrap and an input lead on which we are interested to see the dynamics. And a very simple way to do it would be something like this. You have a chain, let's say an antiferromagnetic chain, and then you have a short piece of chain here, which could be a bistable bit, so an even numbered system, in this case also antiferromagnetic, that can be in either of 2 Néel states. And then the idea is that this thing is weakly coupled to the rest of your chain. So the J inside your chain and the J double prime here inside your structure, they don't need to be equal. You could choose them equal, but in any case, they have to be much bigger than J prime here. And J prime would be a small number. It could either be ferro or anti-ferro. That's still general in this case. So the idea would be you place your STM tip here, an excitation starts to move, and then you see whether this thing flips or not, depending on the length of this chain or the position of the tip, or well, all kinds of geometries that you can think of, not only linear. Now let's see, I mean, of course, we're not the first one to do remote detection in STM, so let's see what other work has been done in terms of something similar to this. So one of the most beautiful papers in our field that came out during my PhD was the molecule Cascades, amazing work, where carbon monoxide molecules were arranged in a very complex pattern. And basically, this is a molecular form of dominoes. So you put them in a state as if you put the domino tile straight up. And then you have 2 inputs here. And then you knock the first molecule over. You just knock it to the next lattice site. And that sets up a chain reaction. And then a whole line of molecules falls over, and that happens over here. So you see that these 2 arms have now collapsed, and the other ones have not. And then you also do the same thing with this input, and the whole thing here collapses. And then this thing was very carefully designed to have all kinds of fan-out and crossover structures and logical gates, so that the outputs are logical effects of your input states. It's really atomic scale logic, but not magnetic. Right? This is just position of molecules. Another beautiful work, also a classic, I would say, is the paper by Alex Kajatourians, back then still in Hamburg. where he does something comparable. So now we have a logic gate composed out of magnetic atoms, antiferromagnetically coupled. So here you see again that spin polarized contrast. You see, if you look closely, dark, light, dark, light, dark, light. But then depending on the input states of these magnetic islands over here, that they are slightly more macroscopic islands that the chains are coupled to, which by the way is already quite special, that you can couple an atomic chain to a macroscopic island. But then depending on the two states of these islands, you have a certain output here, and that would be an AND gate or an OR gate or whatever you design. Beautiful example. However, both of these examples, I want to point out, are, so in each of these cases, the output is a direct function of the input. So to put it a bit blunt, you really wouldn't need to read out the output anymore if you have already read the inputs. If you know the inputs, you know what the output will be. And it's still a fantastic piece of logic, but the output is a direct function of the inputs, right? There can only be one combination. So let's look at some other examples here. So this is a bit more recent, a paper in Sebastian Lode's group, where there's a larger structure here of magnetic atoms, even numbered, that can be in two different Néel states, and then an output lead here. And then you're not looking at the magnetic state of the output lead, but you're looking at the switching rate of the magnetic state. So this is an odd numbered structure, so it would always want to be in principle in the high-low, in the up-down-up state if you have an external magnetic field. You see that also here in contrast, you see large, smaller, large, right? But it can still flip back and forth between its two states, and depending on what state this one is in, it will do that faster or slower, and you can beautifully measure that in the pump probe spectra, where you measure the lifetime of this state. So also here, you are not measuring the magnetic state, but the lifetime here is again a direct function of the input. And then there's this paper by Fabian, he's today in the audience, and this is even more recent, where they perform ESR. And so this actually allows me to introduce the newest technique in our field, ESR, electron spin resonance, where you can look not at the magnetic state of individual atoms, but at the resonance frequency of such an atom. I'm sure that in this colloquium series, we will have more examples of this, so I will not spend too much time on this. But for the purpose of the remote detection here is that you have a holmium atom, which is stable, just like this bit over here. And then you have a readout atom, which would be the iron atom. And in this case, you probe the resonance frequency of the iron atom, which shifts depending on the magnetic state of that holmium atom. So they are much closer to each other than here. So in this case, you're really measuring the dipolar stray field of the holmium atom. It's quite amazing. But also here, the resonance frequency on the iron atom is a direct function of the state of the holmium atom. So the output really tells you exactly what the input is. Now,
sorry, I think that there's another question. So, Jan, go, you can ask. All right, or maybe not. All right, sorry, perhaps he just pressed the button. So, you can continue, sorry.
Okay, just let me know if there's a question anytime. So I want to remind you, so what we want to do is we want to have an output gate that doesn't tell you the state of the input, but it tells you the history of the input. It tells you whether there was in the recent past an excitation on the input, which means that even if the input has fallen back to its ground state, the output should stay flipped. So the output is not a direct function of the input. The output is a direct function of the history of the input, but for a certain state of the input, the output can be in different states. That is a key element to the experiment that I'm presenting here, and it's different from what I've showed so far. Now, actually, there's one experiment that does show that, and this is work in Matthias Bode's group. This is not in magnetism, but it's a very nice experiment. So here they use a molecule that can be in two different geometrical states, tautomerization states, and they are degenerate, but they are also bistable. So it's either in one or the other, and it takes some energy to knock it from one to the other. And then, so they prepare the molecule in a certain state, and then they park the STM tip somewhere else, either with a barrier in between or not, or anything else, whatever you want to do. So you park the STM tip somewhere else, you make a pulse here, and as a result, you have a surface wave of electrons traveling, and that either flips or does not flip this molecule to the other state, and then you have time later in retrospect to visit that molecule and check whether it has flipped. So in this case it was flipped, and in this case it was not flipped. So this really is what we want to do, but then with magnetic atoms, right? To look at collective quantum dynamics. Okay, so let's go back to the idea. So the requirements that we have is that the output state must be independent from the input state. It can be in either of the two output states, no matter on what the input is. And the output should have a long-lived memory that records the history of the input state. And if you look closely, you actually see that this kind of naive idea that I put down here wouldn't really work. It might work, but it's not ideal, because if you apply a magnetic field, then which you need for your spin polarized contrast or whatever, in principle, this one would be, the two Néel states on the output would be degenerate, except that you couple it to some input lead, and that favors one state over the other here. So you really want the two states here to be completely degenerate, even though it is coupled to an input chain. And so the idea that we had in the end, and this was a key idea to make it work, actually this was an idea of my postdoc, David Coffey, was to have on the other side of your output lead a counterbalance, or you can call it a counterbalance or a reset or another input or whatever you want to call it. But the idea is now as follows: you have an input lead, which can, by the way, be way longer than 3. This is just the beginning. It can also be much longer than the reset lead. But you have an input lead, you have your output bit that can flip between two states, and then on the other side of the output you have a counterbalance or reset, which should be odd numbered. So the input is odd numbered, the reset is odd numbered, the output should be even numbered. And now you see that let's say that, for example, the J prime here that couples between your leads is ferromagnetic. This means that if this one is in the up-down-up state, which it would be due to the external field, and this one is in the up-down-up state, then in this situation, the left junction here would be what we call happy, right? Because they're ferromagnetic, and the right side would be unhappy. But obviously, if you would flip this thing, then this one would be unhappy, that one would be happy, and it would be equal energy. So here you see, this is actual data. So you see a spin polarized contrast here on this structure that we call a 383. You see the output lead here in its two different states that should really be degenerate. Okay, so how does this spin wave detector work? By the way, this work was by mostly done by my PhD students, Robbie Alberts and David Coffey, who I already mentioned, and will soon appear in communications physics. So how does this work? Well, I've drawn here the structure again. I've shortened the output lead just for convenience. So let's say that we start in this situation where the left state is happy, the right state is unhappy, and the two Néel states are degenerate. But I am in Néel state A, right, where this one is up or red. Now I make an excitation on my input lead. So here I've drawn the input lead completely flipped, but it would also work if I make an excitation, and an excitation travels in this chain and only slightly flips this one. So it slightly flips it from red to almost red or all the way blue. In any case, this lead now, or this junction would become less happy than it was before, and the right side was already unhappy. So now the structure stands to gain energy by flipping the output leads to the low energy state, to the other Néel state. Right, so now it says unhappy, happy, or in any case, not entirely happy and unhappy. And now if I flip the output, that will be happy on this side and happy here, and I'm in the lowest energy state. And this will remain like that even after I take away the tip. So this one falls back to its ground state. Now it's unhappy, happy, but this one will remain switched and will remain in Néel state B. And then I can reset the structure, and of course it's completely symmetric, so you can also just say I'm going to do the same experiment on the right side. I make an excitation on the right side, or I flip the right lead. I cause a situation that's unhappy, unhappy. So that means that the structure can gain energy by going to the other Néel state, and indeed it does so, and then you are back to your original state. That's the concept, the cycle, let's say the duty cycle of this, what we call spin wave detector. Okay, so this means that if I would do this starting on what we call the happy side, it should flip. If I start on the unhappy side, it would not flip, right? So this is a ratchet behavior, but it would not work if I start on the unhappy side. So if let's say I start in step 3, but then I put my STM tip here on the left, then by flipping this lead, I make it happy, happy, and then it doesn't want to flip because it's already in the happy, happy state.
So Sander, there's a question.
Sure.
So Robert,
Yeah, thanks. So what exactly, or is there something specific here that prevents a direct tunneling between two spin states of your detector chain? Is this just a size thing, that if you make it large enough, eventually they will no longer tunnel between them?
It's an excellent question. So this leads back to work that was done in 2012. That was the first example of bistable structures, and indeed. As I showed before, you have, due to transverse anisotropy, you get certain mixing of the states. So the Néel states are not your perfect eigenstates. So you could, in principle, tunnel from one Néel state to the other. But as you add more atoms to your chain, that rapidly becomes less likely. And so indeed, that's why we chose 8 atoms. 8 atoms is enough for quantum tunneling of magnetization to occur only once in many seconds. And that is what we need, right? We need, you need to make an excitation here and then have time for your STM to go here somewhere on this lead and read it out. And well, we can do that in much less than a second. So, seconds is long enough lifetime. Yeah, very good question.
Thank you.
Okay, so let's first test the device. So here we see actual measurement results. So what we do, we first prepare the 383 structure in the, let's say, the happy configuration. And then we bring the STM tip to the input lead, to one of the atoms on the input lead, let's say atom C here. So the numbering is here, by the way, atom C. And then we give a voltage pulse. So we just increase the voltage for a short time beyond the threshold for an excitation. Or actually not necessarily, we vary the voltage. But so we give a voltage pulse, and then we see how this thing behaves. And then as a result of the voltage pulse, we check on the output lead whether it flipped or not, and we repeat that many times. So there's a lot of statistics here. And then you see that if the voltage pulse is very small, below the threshold for excitation, the chance of flipping either from the happy or the unhappy lead is very small. But then as you reach the threshold, which is in the order of 5 to 6 millivolts, that's the anisotropy energy, then you start to see that switching from the happy side becomes quite likely, roughly 80%, whereas switching from the unhappy side also happens occasionally, but much less so only 20%. And then as you increase your voltage, if you increase your voltage, you see that that distribution stays similar, but they slowly converge. And this is because you're making also secondary excitations, and so it becomes less clean in a sense. Now let's look a bit more. So this is the proof that the concept works, but let's look in a bit more detail. So here we varied the width of the pulse. So we fix here the voltage of the excitations so we're at 10 millivolts, so we're here. We have a current of 1.1 picoamp, so that is determined by the tip height, that's also constant. The only thing we vary here is the pulse width. So that means that basically this here is a measure for the number of electrons that tunnel, right? So that is put up here, estimate, order magnitude. So we sweep the number of electrons during the pulse over 4 orders of magnitude. What we see here that if the number of electrons is too low, and by the way, this is all the electrons in the pulse, so also the electrons that are below the threshold. So this is also all the conduction electrons that don't make any excitations. So only a fraction of these actually make an excitation, and then only a fraction of those make enough of an excitation to flip the structure over to the other side. And then we see here that you really need to increase that number of electrons to an order of a few times 10 to the 5 in order to make excitations probable. You can also vary the current, so basically the tip height. So now I leave the pulse width constant, I again leave the voltage constant, but I vary only the tip height. So also here, these numbers continue here. So this is roughly 10 to the 4th electrons per pulse, 10 to the 5, 10 to the 6, 10 to the 7. So that scale applies also to these lower graphs. And then you see the same behavior, except that when you go to very high current, you see that excitations, that it becomes probable again for, well, less probable to flip the happy state and more probable to flip the unhappy state. So the difference between here and here is, so they're the same number of electrons per pulse, except that here the pulse is relatively, now I have to say it properly, the pulse is relatively long and therefore the electrons are far apart in time. And here the same number of electrons is squeezed in a shorter pulse. And thus it becomes more likely to make secondary excitations. You make an excitation upon an excitation, and then you and also what we think might be happening here is that excitations are tunneling into the lead here, and so the output lead is not being flipped because of the state of the input lead, but because excitations are actually traversing into the output lead. Okay. So now let's see. I'm on time, yeah. So how does this actually work? So we've tested the device and it works as it should. Now let's actually do some measurements and let's vary the input length. So here on the left side, I show data taken on a 3A3, so a 3-atom input lead. On the right side, 5A3. The longest we made was 9A3, so I'll show that in a moment. So don't get your hopes up, it didn't go to hundreds of atoms, unfortunately. But let's see what happens here. So this is the probability of flipping either from the happy or the unhappy state on atom A, which is closest to the input, to the output, atom B or atom C. And we see here that for the 3-atom chain, the switching probability stays rather high, but however, it dips a bit at atom B. And there's enough statistics on here to really say that this dip is significant, right? This is really there. The probability of flipping the output due to an excitation on atom B is smaller than atoms A or C. However, on the 5-atom chain, we see that there's a monotonous decrease in switching probability. So here actually, so atoms A and B are similar to here, but then switching from atom C is actually very improbable. Way more improbable than here. So adding 2 atoms on the far side, not on the side where the excitation should travel, actually strongly diminishes your chance to make an excitation, and the chance even further diminishes as you make the chain longer. So let's try to understand this behavior. In order to do so, we did something very simple. We didn't even collaborate with theorists. We did this ourselves. It's so simple. So maybe theorists are laughing at me now for the simplicity of what I'm doing here, but that's okay. So we decided to just look at the input chain, the 3 atoms, and do time-dependent Schrödinger equation calculations. So you start in the, let's say, 2 minus 2, 2 state. We don't take the output chain into account, except that we have an effective stray field on this atom A. That's the only thing that we take into account. But other than that, we forget about the output lead. We only look at the input lead here. And then in my calculations, I make an excitation on either atom C, atom B, or atom A. And then I see how the magnetization evolves by just regular quantum evolution of the spins over time after I make that excitation. So I make an excitation from, in this case, the 2 to the 1, or the -2 to the -1, or 2 to 1. So the left plot here shows what happens if I make an excitation on atom C, and then it shows what happens to atom A, atom B, or atom C. So here you see that at the beginning, at time 0, atom C is not quite red anymore. Atom A is still fully red, and this one is still fully blue. But then this starts to kind of bounce back and forth, this magnon, essentially. It's a magnon in an antiferromagnetic chain. If you make the excitation on B, it's different already. You see faster oscillating, so it's like 2 excitations that counter propagate and then come back to each other, something like this. It's a different behavior. And then this, of course, should be similar to this one, but mirrored. Right. If we do the same calculation for the 5-atom chain, so now I'm not showing all atoms, I'm just showing atoms. So I'm showing excitations on atoms C, B, and A, but I'm showing the evolution of all 5 atoms. I see here that I make an excitation on C, and again, this you should compare to this, right? You make an excitation on C, but here there's just 1 excitation that bounces back and forth in your chain, and here there's 2 excitations that propagate outward and then inward again, and somehow they interfere in such a way that atom A doesn't oscillate as much. So atom A doesn't oscillate by far as much as it would in this situation, right? And that is exactly the reason why, and that is, again, this interference of magnons, that's really what we're looking at here. That's the reason why we cannot effectively switch the output lead if we make an excitation on atom C in the 5-3. Okay, so let's see how that works out quantitatively. So here we see again the data that I showed you before, but now on the right side I see the result of these time-dependent Schrödinger equation calculations. So this is just the same oscillation that you saw before, but here on the left, these open data points are the time averaged magnetization of atom A as a result of an excitation on C, B, or A, right? So this should be a measure for the probability to flip the output chain. And you see indeed this V-shaped behavior here, whereas here you see a monotonously decreasing effect. So this is to show that we think we can say that we actually have a little bit of an idea in seeing the free evolution of quantum spins in a chain as a function of position. Okay, so finally, I promised you to show you the 9A3. The data here is interesting. So now we have input atoms A to I, and then here, depending on the pulse intensity, I think it was the tip height we changed here. You see that you can excite them from further, right? So blue was not a very intense pulse, and then dark blue was intenser, and purple was very intense. But qualitatively, the behavior here in the 9-atom chain is similar to the 5-atom chain for now. Okay, so I have some time left, so I would like to move on to the next topic. So again, this work will soon appear in communications physics. Okay, so the last topic for today is this complete reversal of orbital momentum, the delta m equals 4.
Sander, sorry, so there are a couple questions. So Marcus, you can go first.
Yeah, thank you, because I would like to ask a question to your time-dependent Schrödinger equation. It looks a little bit that this is noisy, or there's quite a lot of structure in it. Can you comment on it?
Not really. I mean, so you mean the small jitters here?
Yes, or is it just a discretization, or can you? I mean, it looks more like data than like simulation.
Right. Now it is simulation, and we try to play with the time steps to see whether the results would be completely different. So if I play a bit with the time steps, I believe the small noise looks different every time. So it is some calculation noise. So if you have the same input parameters, obviously you get the same result every time. But if I slightly change the input parameters, that noise might change a bit. But the overall feature, so the longer oscillations, are really always there and are consistent. For these oscillations, I don't want to make any conclusions at this moment whether they are real or not. The long standing is definitely real. This one is real. Yeah, I would have to check on the other ones. Yeah. But I do want to emphasize that these calculations you should take with a grain of salt. They're extremely simplified. We didn't even take dissipation into account. So that's why we only plot the first 100 picoseconds, because after 100 picoseconds, probably the excitation would be dissipated anyhow to the surface. But it gives you a nice idea of what's going on.
Thank you.
Okay, sure. Yeah.
And then there's another question from Robert. So Robert, you can speak up.
Yeah, thanks. Now, this one's a little bit nasty, I'm sorry, but if I look at the 583 data, and in particular the turquoise data bit of the 983, then there would be a way of reading this and saying what you have here is maybe more related to proximity of the tip to your detector rather than a propagation of an excitation along your chain. So can you test for that in any way, or can you exclude this? I mean, of course, if you look at the rest of the data set, it's quite clear that you can excite from further away, but would there be a way of kind of telling these two situations apart, or can you comment on a possible interference of the excitation signal so close to the detector lead?
Well, okay, so first of all, we are not that close. So tunneling is tunneling directly from the tip to your output chain is absolutely zero, right? So tunneling goes down so quickly that you really do not get any effect due to that. Then there's the tip-induced field that was studied before by, for example, Sebastian Loth, and we actually also did experiments here as a function of tip height to see whether we can switch the input lead by tip field, but that tip field is also due to tunneling of electrons, right? It's an exchange coupling to the tip, so also that we can ignore. Of course, let me think. So, well, let's put it like this: we varied many parameters. We played with the tip height. We played with with the current, with the voltage, and I really don't think that this here is proximity to the, I mean, the simple fact that if you make the pulse stronger, you get the same probability of excitation at atom D here. So, and this is definitely not proximity of detection.
Yeah, that's a very strong argument, of course.
Right? That's, yeah. I hope that answers the question. I mean,
no, that's good enough. Yeah, thank you.
Okay, good. Jose, any other questions on this?
No more questions so far.
Okay, good. Okay, so dessert. So orbital angular momentum. So what we studied in this work, which did appear in the archive last year. First author is Raza Rejali. She's a PhD student in my group. Here we studied iron atoms again on copper nitride. So all the previous work I also showed you was, I think I didn't even mention it, was iron on copper nitride. This is also iron on copper nitride, but now the iron atoms are not on the copper sides, but are on the nitrogen sides. So on the copper sides, you would have let's say an actual anisotropy in plane, because your nitrogen atoms, your nitrogen ligands are horizontally to the side of your iron atom. But here your iron atom sits on a fourfold symmetric side on the copper nitride, the nitrogen side. So this is top view, this is side view. You really see it's fourfold symmetric. Now, before I want to move on, I want to immediately point out that this is almost identical to work that was previously published by the IBM group. So here we have iron atoms on magnesium oxide, the surface that is used for all these ESR experiments. And so iron is here on the oxygen side of magnesium oxide, and it's really the same structure. And there was, of course, the other paper by Eliana Rao, where there was a cobalt atom on the same side, and also there you have similar structures. So there's several examples here of this work. Now, why is this interesting? If you have such fourfold symmetry, or in general, if you have high symmetry on a surface, your orbitals regain their degeneracy, or the degeneracy between the orbitals is not broken. That's another way of saying it. So you have your dxy and dx squared minus y squared orbitals, which would be broken. The degeneracy of them would be broken if there's low symmetry, but in high symmetry you to a good extent regain that degeneracy, and as a result your ML states for out of plane magnetization, so MLZ, are good eigenstates again. And another way of saying is that you unquench the orbital moment. So in general, when you put a magnetic atom on a surface, your orbital magnetic moment may be quenched due to breaking of symmetry. But if you put it on a position where you have high symmetry, you do not quench the orbital moment. So you have an unquenched orbital moment. You have a real orbital moment that is basically electrons running around here in this donut. That is a way of looking at it. And it's similar here in this shape. Okay, so what does this result in? Well, it results in very strong anisotropy, because anisotropy results from your spin-orbit interaction, and if your orbital moment is unquenched, the spin-orbit interaction will also be strong. So here we see multiplet calculations for our situation, and then on the right here in the paper of Suzanne Bauman's case, the iron on NGO, and we see a very similar behavior. So the lowest 10 states split up in two quintuplets that you can read as follows. So they are all the LZ equals plus and minus 2 states. And now I hate to criticize other people's work, it's a detail, but here I think these LZ and SC should be expectation values of LZ and SC. For here, there's the LZ equals plus or minus 2 states. That means that this state should still be L is plus or minus 2, but it is a superposition of them, causing an expectation value LZ to be 0. I think that is the case. In any case, I know that is true here, right? So we have the LZ equals 1, plus or minus 1 and 0 states are way high up in energy. Those 15 states they shoot up in energy due to the crystal field. You only have the plus or minus 2 states left. And then here you see that for the lower quintuplet, you have your, let's say, your normal spin parabola, plus or minus 2, plus or minus 1, 0, but all parallel to your LZ equals 2, and also here it's expectation value, but this is still LZ equals plus or minus 2. And then the top quintuplet is an inverted parabola. You plus or minus 2 for spin, plus or minus 1 for spin, 0 spin, but anti-parallel to your orbital magnetic moment. Okay. Now, if we take a spectrum on such a atom, we find the following. So first of all, in the past, we tried this also, and we didn't see much, but it turns out that it's important that the tip is somewhat functionalized. The tip has to have some magnetic atoms on there or whatever. So this doesn't always appear, but it appears often enough. And when it appears, it's very clear and always at the same energy. So it's quite real. And what we see is, first of all, a fairly high energy excitation. So in the order of 20 millivolts, we see a beautiful symmetric excitation appear here. And I want to point out that for a single iron atom on the surface, this is already a very high anisotropy energy. And that is because of this unquenched orbital momentum. So this excitation here can be explained very well in terms of excitations from the ground state to state 2, or from the first excited state to state 3. Right? So that's also shown here, these two excitations. You would expect them to diverge as a function of field, right? That's also shown here. As the field increases, you would expect those excitations to diverge. And indeed, they do diverge as you would expect. Now, you might ask, why is it such a sharp peak? Well, this can be explained very nicely in terms of dynamics. So as you make an excitation, for example, to state 2, there is a larger probability of ending up in state 1. And in your spin polarized contrast, that totally changes your elastic current. And therefore, you have this strange nonlinear behavior in the spectroscopy. So this is discussed very well in a paper by Sebastian Lode's group, PRL, a few years ago. And we did that analysis also, these calculations, what you would expect in terms of line shape for these atoms here. And you see that we can quite well reproduce here the features. By the way, there's two models used here. On the one hand, there's the point charge model, and on the other hand, the spin orbit model. That I should have pointed out in the previous slide here. These multiplet calculations, you see dots here and lines, are two different sets of calculations. So if I'm not mistaken, the dots are the point charge model, the lines are the spin orbit model, and they really show exactly the same behavior, right? So this is not just dots connected with lines, it's two completely different sets that make up these calculations. And then you see indeed that depending on, no matter which model you use here, you see that same very strongly nonlinear behavior. And that means you can also calculate then the occupation probability, so the population of your states as a function of your applied bias voltage. Okay, that's this first excitation, a regular spin excitation, I would say. You flip you excite the spin, but you leave the L unchanged. But now let's focus on this higher excitation here, around 70 millivolts, which is also quite clear. So this one we interpret in terms of a rotation of your angular momentum. That would be an excitation either from 0 to state 8 or from 1 to state 9, which means that you go from -2 to -2 plus 2, so you flip LZ, or you go from +2 plus 2 to +2 minus 2, so you flip LZ. You only flip LZ and you L, and you don't flip S. Why do we associate it as such? Well, there's several arguments for this. So first of all, the energy matches. Now you might say, well, okay, but these models are not perfect, so it could also be another excitation. Fair enough. But then you can also calculate what the probability is for all your different excitations based on all the selection rules and what have you. And then we find that after these excitations, after the yellow ones, the red ones are the most probable ones, followed quite a bit later by 0 to 7. But since this one is more probable and it matches the energy that we would expect, we really believe it's this one. Then you could also argue, but wait a second, maybe we're looking at excitation, a secondary excitation from 2 to 7, for example, or from 2 to 6 or whatever. This could theoretically also be possible, but the transition intensity for those excitations is already 7 times lower than the red one here, not taking into account that the probability of being in state 2 is reduced compared to state 0. So we really can neglect those excitations. And then the last argument we have is that these excitations are supposed to behave a certain way in magnetic field, and we see that that behavior in magnetic field is visible to the willing eye, I must admit, but it is visible. So the lines here are the calculations, and the colored lines are the measurements, right? So within the error bars, there's a decline. So what are these excitations? Well, this would be a delta MS4 transition, right? So you would think, well, is it possible? Well, the way to look at this is as follows. So a spin excitation, so all these excitations are co-tunneling excitations, which means they involve an electron tunneling onto your atom and an electron tunneling off, basically simultaneously, or first the one or the other. It doesn't really matter the order. So that means that there's an intermediate state which leaves the atom charged, which is way high up in energy. It's a virtual state, either negatively charged or positively charged, depending on whether the electron goes on first or off first. But in any case, all these excitations are co-tunneling events. So a spin excitation would be that you have your orbitals here that are split by your crystal field, and they're mixed and whatever, but still you have a certain dimensionality. A down electron tunnels onto an orbital, and off that same orbital, an up electron tunnels off, which means that you leave the orbital moment the same, but you flip the spin. Now, an orbital excitation would be that an electron tunnels onto, let's say, a +2 state and tunnels off the -2 state, and then you flip your orbital moment. So the spin is the same here, the number of arrows pointing up is the same, but now you've went from occupation in the -2 to the +2, or vice versa. That would be a delta M=4 transition. And now you might ask, but wait, how does this work? Can the electron actually carry that angular momentum? Can an electron, we know that electron, when you make spin excitations, they carry a spin of maximum half. So they can accommodate an excitation of a maximum delta M=1. How come that the electron can carry an angular momentum here of 2, apparently, and carry off an angular momentum of -2? Is that even possible? And if you think about it, you can. And I'm going to make a very silly argument for that. And that's this slide. So here on the left, I've depicted our solar system. And I actually spent quite some work on it. So all the planets have the correct sizes and colors and positions, and Saturn has rings. So I really want you to appreciate the work that I spent here. So now imagine you have the solar system, and we have 2 heavy asteroids inbound from outer space into our solar system, and they have the same weight and the same velocity. They only have a slightly displaced trajectory. Then we would say that from the viewpoint of the sun, asteroid A has roughly twice the angular momentum as asteroid B, because it would pass the sun at twice the distance, roughly. Right? But that is just because we happen to choose the sun. What do the asteroids care that we choose the sun as our frame of reference for orbital angular momentum? These asteroids are just flying around in free space, and they carry as much angular momentum with respect to the sun as you want. Right? So the point of this is that an object that comes from far away, classically at least, can carry an arbitrary amount of angular momentum because it doesn't have the same frame of reference as you have. So an electron inbound to our atom does not know that we want to have the nucleus of the atom as the reference point for angular momentum. Now you say, okay, that's classical. So how does this work quantum mechanically? Well, quantum mechanically, I would say the metal is composed of all kinds of S and P orbitals that are hybridized. And if you hybridize many p orbitals together that all have L1, you can have hybridized states that have much bigger L. So electrons really can have very large angular momentum, I think, when they're incident to your atom. And then in this situation, although in real life it's not very likely, but a heavy asteroid that has the same mass as the Earth could actually collide with the Earth, knock the Earth out of orbit, and then continue after the collision, could continue orbiting in the opposite direction that the Earth used to do. Right? And that would be exactly, you say that is improbable, and luckily it's improbable for the Earth, but it is not very improbable in our case, because I claim that is exactly what we see here, about, I don't know, 10 to the 5 times per second. That would be the same here. An electron comes in with +2 and leaves with -2. So, and then you leave something spinning here in the opposite direction. So that would be my explanation here. So this is actually, of course, not very profound. It's actually quite logical that this would happen, but still we're not used to thinking about it this way. And I think it's useful to see it once and to actually have observed such an excitation and confirmed that it exists, and that you can indeed make arbitrary large delta M L transitions. Okay, so this concludes this paper. Again, it's on the archive at the moment. And that also concludes my talk. So after having given a short introduction to our field, I've discussed 2 topics. First, the remote detection of spins, spin dynamics in our spin wave detector device that we have built. and then the full reversal of the orbital angular momentum delta ms4 transition. Let me conclude by thanking many people. So the main people here on these papers were Raza Rajali, Robbie Albertse, and David Coffey, and collaboration with Fernando Delgado and John Gonzalez. I also thank all current and former members of my group, and I confirm support from the European Research Council and from the NWO, which is the Dutch Organization for Scientific Research. And I thank you for your attention today.
Yeah, thank you.
Yeah, thanks for a really nice talk. I don't know, I guess we will take some questions. So we're done about an hour now. There were already some questions. I think also if people have places to go to, it's not too difficult to leave from a virtual meeting. So let's just take some questions here. If there are some.
Question. Can I have a question? I'm Leo.
Sure, Leo.
Okay.
Yeah.
Sander, this goes more to a side remark that you made, but I find it quite interesting and important. So, and that's the question whether your intermediate is charged or not, and if you have sequential tunneling of electrons flipping your spin, or just a virtual occupation. And you said it is charged, doesn't matter if it's first positive or negative. And what are you sure about that? Are there any experimental proofs of that?
Hold on. Well, so there's no experimental proof as far as I know, because these would be really virtual excitations. So the energy, the charging energy is in the order of volts, electron volts, right? And the voltage we're applying here is in the order of millivolts. So obviously we're not applying enough energy to make such a transition. So it's really virtual. So it's Heisenberg, right? You borrow the energy, and if you borrow it, if you pay back quickly enough, you can borrow more. That's the logic I always learned. That is what's happening here. So as far as I understand, this co-tunneling picture is a very established theory, also used a lot in quantum dots, semiconducting quantum dots. So this is not really in our field only. The inelastic co-tunneling is widely studied, and it applies very well to our case. But a direct experimental proof, I don't think there is. No.
Hey, can I ask a question?
Daniel, sure. Yeah.
Yeah. Sander, hey, thanks for this very interesting talk. I would like to ask a small question on your, let's say, last topic on a change of the orbital momentum with 4. To prove your theory, would it help that you try to functionalize your tip with, say, last atoms, which are from the transition metals, where you have valence states, which are basically d orbitals, where you already have more chance to have a nice orbital momentum of 2?
That's certainly an interesting direction. But that would mean that you can tunnel straight from a d orbital across your tunnel junction. And I'm not even so sure whether that is possible. So I'm not saying it's impossible, but so all the experiments we do, we have a d atom on our surface. And then we do inelastic tunneling, but it doesn't necessarily mean, so this here doesn't necessarily mean that the electron tunnels straight from the tip onto the d orbital and then out into the surface. It can also go tunnel from the tip onto an s or p orbital of the atom, then go on the d orbital of the atom, and then leave the atom. Right? So the d orbitals are more confined to the atom than the s and p orbitals. So I'm not sure how likely it is that an electron would go straight from the tip to the d orbital, and also vice versa.
Okay, but in your explanation, what would then be the mechanism that, say, you are already on your substrate in a p orbital and you have to go to d orbital? This angular momentum change of 1.
Yeah.
Where does this come from?
That's a good question. So, well, first of all, the s and p orbitals on the atom on the surface are also hybridized. So they are not necessarily confined, so the angular momentum could be bigger there. Also, it could go very fast. So that means that delta L is not a good quantum number, but you're kind of doing the same sort of cheat as you do in terms of the virtual excitation here. I don't know, to be frank. That is so maybe. Okay, let's go one step back. So this whole story here, I'm just showing here that in principle there's no reason to disregard the possibility of larger L electrons coming along. It doesn't mean that I explain all the necessary steps. So I think this is the starting point of interesting research where we have to think about how does this actually precisely work, the exchange of angular momentum. I just want to point out that there's no a priori reason to say delta M for orbital angular excitation should be 1 and nothing else. I think there's much room for allowing larger delta M excitations.
Yeah, I agree, but it should somehow in the entire system more or less be conserved, isn't it?
In the entire system should be conserved, obviously, but that entire system contains the metals and all the electrons in there. So that's
okay.
Or in this case, the entire universe, actually.
Yeah. Okay, thanks.
Had a next question.
Hi, this is Sebastian. Can I ask a question?
Can we have Roman first?
Oh, sure, totally.
Yeah, and then Sebastian next.
Thank you. Excellent talk, Sander, very interesting. I have a question regarding the first part, namely on the coupling strength between your input and output structures. So you had this nice illustrative sketch with the different coupling strengths. Do you have an idea on what the coupling strength actually is? Or, I mean, can you get that out from simulations?
Yeah, sure, the coupling strength inside the structures has been very well studied. So these are two unit cells apart along what we call the nitrogen row of the copper nitride. And off the top of my head, this is in the order of 0.7 MeV anti-ferromagnetic coupling. The coupling, this is 3 unit cells apart along the same direction. That coupling is slightly harder to measure because you're looking at a tiny shift in terms of excitation energy, but we estimate it to be at least an order of magnitude smaller than this, or let's say an order of magnitude smaller. So order 0.1 or smaller, 0.07 or 0.05 MeV ferromagnetic coupling. Yeah, and that is based on experiments.
Mm-hmm. Yeah. I mean, how would the overall picture change if you start, or did you play with this coupling strength? So let's say just leaving 1 or 2 voids and not 3, or increasing.
Yeah, we played a bit with it, although the thing is that in order to do those test experiments, you have to build the entire structure and do statistics on it, and only then can you say whether it works or not. So to really check another coupling here, you would have to build the entire structure with a different coupling and do the entire experiment. So while we did, of course, explore different coupling strengths, in the end, after having measured all of them and having done some modeling and calculations, we came to the conclusion that this would be the best approach or the best design, and then we started from that design. So we didn't build the entire structure for different coupling strengths.
Thanks.
But that would obviously be a very interesting next step to explore.
I think Sebastian had a question.
Yes, and so first of all, Sander and Peter, thanks very much for making this colloquium. It was one of the most enjoyable online colloquia I had so far.
Thanks.
So thanks a lot. That's really great.
And without disturbances.
So the question I had was for the remote detection thing. Yeah. Sander, way back when you and I did these spin pumping measurements on the manganese chains or manganese dimers, right? Like the model we used said that the spin excitations on there live only for very few picoseconds and then they decay. Yeah. So what is different about these iron chains that makes it reasonable, or that makes it apparently such that that these magnon excitations live so long?
I don't necessarily say they live long. I don't think we have done so we varied the pulse width, so that we did, but that was just to increase the number of electrons that participate to increase statistics. I don't think we have any direct measures on how long or short-lived they are. They can actually be quite short-lived. But to give you an idea, how do I? Okay, now I have to go through some slides here. Sorry about that. Where am I going to? Yeah, so yeah, I want to look at the as a function of pulse width. Ah, man, all these animations here. So, okay, so the idea is that a single excitation. Well, okay, yeah. So at some point you see here that if you make the current large enough, you see that the excitation probability goes down again on the happy side and up on the unhappy side. So one explanation for this is that you have excitations upon excitations. Mm-hmm. That start to make, well, not just a single magnon. So the idea is that if you, before this area here, the electrons are far enough in time apart, the excitation events are far enough apart in time that you make a single magnon excitation and it dies out, and then you wait some time and you make a new one. Only when the excitation events come fast enough after each other, you get excitation upon excitation. And that is when you make the current real big. So here you can, if you look at those currents, you can get an estimate of how big you would have to make the current in order to make secondary excitations before the magnons die out. And I would have to look at the numbers here to see how long that would be. But I think they're still shortly lived. I hope that answers the question.
Yes, thank you.
Okay, yeah.
Yeah, so there's another question by Robbie. Robbie, you can go.
Hi, maybe I can comment on that last question as well. So we did some calculations and we found that the excitations live approximately 7 picoseconds in terms of lifetime. So if you take several lifetimes as a maximum range of how long these excitations live, you come in the order of 20 picoseconds. And so we basically, in the next slide, I believe.
Okay, hold on.
Yeah. The ones with the calculations, please.
Yep. This one or the one with
the next one?
This one.
Yeah. So if you take the average of the first 20 picoseconds, those are actually the data points you see on the left. That also explains why on the right, for the 583, the light blue one, E, even though at around 100 picoseconds, it seems to diverge quite a bit more from the two than the other ones. Since we only look at the first 20 picoseconds, which again is 3 lifetimes, so 95% of all the excitations died out at that point, you can see that there, E indeed is quite a bit smaller, which corresponds to the data point you see in the third image.
Thanks, Robbie. This is
yes.
that helps. Yeah.
Thanks, Robbie. That helped. That I didn't get that. So that means you really need only 20 picoseconds of coherent dynamics to observe these effects you see there. That's quite cool.
I think so. Yeah. And that is, of course, I mean, that shows how necessary it is to have a device with a memory, because nobody can move the tip in 20 picoseconds and do a measurement, right? So this is that's the point of the experiment. Yeah.
Can I have another question?
Yeah, sure. I think. Sorry. Yeah. Okay. Sorry. Go on.
Thanks. In your last experiment, where you had this peak at plus and minus 25 millivolts.
Yeah.
So there was this pronounced asymmetry of the peak height depending on the voltage.
Yeah.
And do you know why that is? And could that be related to which virtual charge state is occupied?
Okay, the first question is, can we understand the nature of this asymmetry here.
Yeah.
So again, I want to point out, I don't have the reference here, I'm sorry for that, but there's a PRL 2017, Sebastian, I think, where this is explained beautifully. So from Sebastian's group. The idea would be that your tip is polarized. And so if you, depending on whether you apply positive voltage beyond the threshold or negative voltage beyond the threshold, you favor excitations out of the ground state or further into the ground state. So you see here that if I go to negative voltage in this case, I pay enough energy, and all of a sudden I really go from the zero state, the ground state, I start to occupy the one state, right? So I really start to occupy the other state because my spin polarized current provides the right electrons. So let's say I need down electrons to do that, and I provide down electrons. If I invert my voltage, I extract electrons. Well, here I extract electrons from the atom. Here I inject electrons into the atom. So that means that here I would be injecting the wrong type of electrons to make the excitation, and as a result, I'm only putting it more into the ground state, or not so much out of the ground state. So the occupation on this side doesn't change so much, whereas the occupation changes dramatically on this side, and that in combination with the spin polarized contrast gives you a very large change in the IV curve that you jump to on this side as respect to this side. So the nature of this asymmetry is really the polarization of the tip, and is not, as far as I understand, about the positive or negatively charged virtual state.
Okay. No, sorry. Thanks
no
for
problem.
the explanation.
Yeah.
Okay, I think if there are sort of no immediate more questions, and what I would propose is that we kind of finish the formal part. We can leave the Zoom meeting open, so if you guys want to chat to each other, that's no problem. So thanks everybody for coming, and thanks for the interest. And there will be a colloquium next Monday by Katharina Franke. So you'll hear, well, we'll see you next Monday, and we will remind you by email and other formats as well. So thanks everybody, and now I think we can just have free discussion if people want to do.